I can't speak in person today, but yeah, I mean, Clemens already has just told you about a lot of what I'm going to talk about now in more detail, and so I can actually build on something what he said. Yeah, I will start with a small motivation, and then I will I will introduce a systematic method of doing post-Newtonian expansions for describing quantum systems under gravity. And I will give two concrete examples, and then in the end I will conclude. And if you want to have a more detailed look at this, you can look at this review article, or also for the spinner particle here. I will have some more references later. Okay, so let's start with the general motivation in the beginning. So let's say we have some kind of quantum system, like a typical atom or something, and we understand this quantum system in the absence of gravity. And then we want to understand what happens if we put this atom in a gravitational field. And so this is what we wish to understand. So how does a typical quantum mechanical system respond to the influence of an external gravitational field? And by saying external here, I really mean that we treat this as a background field. So we have a test quantum particle or test quantum system in an external gravitational background field, and we neglect the back reaction or anything related to that. And the external gravitational field is also classical, so we are not doing anything related to quantum gravity here. But having said this, we still consider a general spacetime metric, so including the Newtonian potential, or like post-Newtonian effects also of that, gravity-magnetic effects, and gravitational waves. And actually, this picture I put there is a little misleading, because there it looks like a very big gravitational field, but actually what we will be interested in are weak gravitational fields. And so in our group in Hanover, the group of Domenico Giulini, or Nico as he's called, and myself, I'm a postdoc in his group, and also did my PhD there. I mean, we do different theoretical work in gravitational physics, but in this area of quantum mechanics under gravity, we have a very specific research area that we pursue there. Namely, we look at quantum systems in weak gravitational fields, so in post-Newtonian gravitational fields, and we want to develop systematic descriptions of such systems from first principles. And in doing so, we take a kind of conservative approach to the problem. So we want to base everything on well-established current standard physics. And we want to use established language for discussing quantum physics and gravitational physics. So for example, as Clemens said in his talk just right now, we developed this atomic Hamiltonian that I'm going to present in some detail, which just takes the form of a typical Hamiltonian as you would use in quantum optics, just with gravitational corrections in there. And well, we want, as I said, to derive complete derivations. We want to make complete derivations of such systematic descriptions that may then be applied to describe experiments. For example, like describing these atom interferometry experiments. And actually, Michael Werner, who is in the audience and who has the poster that was advertised a few times now, he is actually currently working on really adapting this to the description of the real experiment in the VWA Tower in Hanover, where they want to build a 10-meter atomic fountain and do atom interferometry over the course of 10 meters. And yeah, and that's all related to this collaborative research center DQMAT, which stands for Designed Quantum States of Matter, which is based in Hanover and at PTB Braunschweig, and yeah, and also at SAM, actually, in Bremen. Okay, so that's the general motivation. But now I want to go into some more details. So let's look at, I mean, I mentioned before that we are interested in all kinds of gravitational effects, but let's for now just look at the Newtonian potential. So we can just include the Newtonian potential into a quantum Hamiltonian in the usual way. We just add the potential. And this was first tested in the famous Cow experiment, or Colella-Oberhauser-Werner experiment in 1975, where they measured the influence of the gravitational field of the Earth, of the Newtonian gravitational potential, on neutron interferometry. they had a small Newton interferometer, and they tilted it in the gravitational field. That's this angle phi on the x-axis, and then they got this interferometric pattern here. And well, today the most sensitive device for doing or for measuring the gravitational field essentially is atom interferometry, which also can be to lowest order described by just adding the Newtonian potential to the quantum Hamiltonian describing the atoms in this case. But we can wonder, okay, we know that GR or modified theories of gravity are nonlinear theories. So even if we know that the lowest order term will be just a Newtonian potential, we know that, or we should expect that we get some higher order couplings in there. So we should get higher order terms, like terms with phi squared or something similar in there. And so the question is, what do these terms look like? Even if we only focus on the Newtonian potential and not on any other gravitational effects like gravitational waves or so on. And one easy way of getting an idea of what these couplings should look like in a heuristic way is that we start with the simple Newtonian description, and then we include relativistic effects, so to say, as you learn them in your first course on special or general relativity. So what effects could we include? Well, we could include shifts, frequency shifts, like Doppler shifts related to special relativity, so to movement of the emitting light source and of the detector or the atom with respect to each other. Or we have gravitational redshift of light. We could also include time dilation of observers on different world lines with respect to each other, like special relativistic and gravitational time dilation. We could include the idea of the mass defect that Clemens also mentioned, that energy is equivalent to mass, and so also internal energy of an atom or of some system should contribute to its total mass, or anything you can imagine. And one example is to take a composite system, like a system that has some center of mass degree of freedom and some internal degree of freedom, and put this under the influence of gravity. And then one idea how to motivate post-Newtonian effects of gravity in this system is to say, okay, let's assume that the center of mass degree of freedom is more or less localized and moves on a specified world line. For example, in atom interferometry, that's essentially the case. I mean, we put it in a superposition of two different world lines, but let's just focus on one. And then we could say, okay, we can now, we know that if we would take a classical clock and move it along this world line, then this would measure the classical proper time of this world line. And we can compute the proper time, and so that's the physical time passing on this world line. And so the idea would be that the internal degrees of freedom of the system evolve with respect to this center of mass proper time. And this would then obviously lead to a coupling between the internal and center of mass degrees of freedom, because if I move on this world line or on that world line, influences the proper time, and so the time with respect to which the internal degrees of freedom evolve would change. And one very famous effect proposed based on these ideas is the dephasing of large superpositions, for example, in atom interferometry, because if you take this atom with internal degrees of freedom and have it in a superposition of center of mass degrees of freedom, then essentially when you trace over the internal degrees of freedom, then you get a dephasing. And in the original paper, due to Igor Pikowski, Magdalena Zych, Fabio Costa, and Czeslaw Bruckner, they called it a universal decoherence effect, which has been highly debated. And let's say it's not really decoherence because the visibility will decrease and then again increase. But we have this dephasing effect due to these post-Newtonian couplings, due to the internal degrees of freedom evolving with respect to proper time. And similarly, one can also measure special relativistic time dilation by atom interferometry. Whatever, I don't want to go into too much detail here. But there are some problems with all these descriptions. So, as I said, this idea of deriving these couplings is based on assuming semi-classical world lines for the center of mass degree of freedom. This is a picture from this universal decoherence paper, and they really draw the world lines. Even though they are a little bit fuzzy here, we still have these world lines. So for these heuristic descriptions to work, we really need semi-classical notions. And there are some problems with it. So the first one is, I should probably, I start with the second one. So the more fundamental problem is that, well, if we need to use semi-classical notions to understand this, then we are obviously restricted to the situation where we have semi-classical states. And so we don't know anything, or these methods don't help us anything to understand the situation for more general quantum states. And the other objection could be that if we want to be able to speak about a semi-classical center of mass world line, well, then we need somehow to be able to speak of the center of mass state for itself, ignoring the internal state. So I don't think it's quite true that we really need to assume that the state separates, but we need to be able to define or to speak about just the center of mass state, and this is the case even though these couplings that will generate entanglement are the point of interest. And so it's not completely clear from the beginning why this should really work well in a complicated situation. And what is even more an even worse criticism, perhaps, is that using these heuristic descriptions, we have no guarantee that the relativistic effects we include are complete or independent of each other. So it could be that we forget some, or it could also be the case that we double count some. For example, the frequency shifts that I mentioned before, like Doppler shifts or gravitational redshifts, can be seen as just effects of time dilation for the different world lines of the observer and the emitter of the light. Or also this internal-external coupling that I mentioned before, that I motivated from time dilation, is also the same that you get from the mass defect. So if you just take the Hamiltonian for a classical particle, p squared over 2m plus m times phi, but replace the mass by mass plus internal energy, then here we get a coupling between internal energy and center of mass position in this case, and here between internal energy and center of mass momentum. And this will be exactly the same coupling as the one before, when one works it out and just the coordinate transformation and so on. And so if we were to include both the mass defect in this heuristic way, just replacing the mass by rest mass plus internal energy, and the time dilation from before, then we would have double counted this effect. And so really, to make reliable predictions that we can use to analyze experiments, we need to use systematic methods which are complete, that we don't overlook any relativistic effect, so to say, and that are redundancy free. Or put differently, we should really start from a full relativistic theory and then just apply a specified scheme to get to our predictions from that, and not start with a Newtonian description and put things in by hand. And that's what I'm going to talk about now in the main part of my talk, which is actually probably shorter than the introduction, or at least, I mean, I think I'm quite good in time. So why and how do we do these post-Newtonian expansions that I mentioned? So as you know, as was also mentioned a few times today, the best available description of quantum matter under classical background gravity is quantum field theory in curved spacetimes. But this is mathematically and conceptually kind of heavy, so the mathematically most rigorous way to do this is to use algebraic quantum field theory. And I mean, one can certainly do that. Christian has shown us how to do this for general linear electrodynamics, even not in a classical curved spacetime, but on this just with a constitutive tensor there. But it's still a very advanced framework. And so the question is there some easier way to do that if we just have weak gravitational fields? And the answer is yes. In this easier situation, we can really do that, because we are just interested in gravitational corrections or post-Newtonian corrections to the Newtonian situation. So we want to have weak gravitational fields, and we will assume that the gravitational field is approximately time independent, so we have an approximately stationary spacetime. And this will allow us to have a notion of particles, because if you do quantum field theory in curved spacetimes, in order to get a well-defined vacuum state such that you really have a Fock representation of your states, then this is only possible if you have a stationary spacetime. And so we will assume that our spacetime is approximately stationary so that we can really speak about few particle systems. And we also want to fix the number of particles, and so we will also assume that all our processes that we look at have such small energies that we don't get pair production or anything like that. So we really restrict to the low energy regime so that we can fix our number of particles. And then, in order to give sense to this post-Newtonian expansion, we will need to introduce some background structures. So we need something that defines a decomposition of space-time into space and time, because we need that for our Newtonian physics, and then for post-Newtonian physics on top of that. And we also need something to tell us what we mean by small velocities, or by small energies, and we need to say what we mean by weak gravity. And this we do by saying that as a background structure, we have a flat Minkowski metric, and we have an inertial observer vector field in this Minkowski metric, and everything will be defined with respect to those. So the space and time decomposition is from the point of view of this vector field. Small velocities are velocities that are small as seen by this observer, and weak gravity means that the physical spacetime metric has a small difference to this background metric. And the way to implement this is then to use adapted coordinates, so adapted to the Minkowski metric and this observer vector field. And then we start with the full relativistic theory, and we expand all fields as I did it here with the metric. So we have some post-Newtonian parameter epsilon that is thought of as a small parameter, and then we expand everything as a formal power series. For example, for the metric, we would start with the Minkowski metric, and then we just have a power series expansion with some coefficients, and we do this for all the fields appearing in the theory that are important for us. And then by expanding the equations of the theory and doing comparison of coefficients there, we get equations at each order of epsilon, and this allows us to, at leading order, so at epsilon to the 0, we get the Newtonian theory, and then at higher orders we get more and more precise post-Newtonian effects of the theory. And very often I will take this parameter to be 1 over the velocity of light, which is obviously not a small parameter because it's not a number, it's dimensionful. So really, when comparing this to experiment, one should really think of some typical velocity of the system divided by c, but I will always only write 1 over c because that makes it easier. Okay, and this one can now apply to different things. And let me start with the example of this atomic Hamiltonian that Clemens also mentioned and used for the description of atom interferometry. So we have a model composite system for a simple hydrogen-like atom. So we have 2 oppositely charged point particles, which can have different masses, but they don't have spin. And in this paper that I mentioned down here, based on a paper by Matthias Sonnleitner and Stephen Barnett without gravity, we gave the first systematic derivation of a complete post-Newtonian Hamiltonian for such an atomic system in a weak gravitational field to order 1 over c squared. And this works as follows. So we start from the classical Lagrangian for the 2 point particles in the curved spacetime, and we have an electromagnetic field, and this we decompose into 2 parts. One part is the external electromagnetic field that we prescribe as given. So for example, in atom interferometry, this would be the laser field that we use to kick our atoms. But it's just a general field solving the vacuum Maxwell equations. And then we have an internal part of the electromagnetic field that solves the sourced Maxwell equations where the 2 particles act as sources. And these Maxwell equations we can solve perturbatively to order 1 over c squared. These we then reinsert into the Lagrangian. Then we can compute the classical Hamiltonian. Then we do a canonical quantization and perform a so-called Power-Zeno-Woolley transformation. That's a standard method in quantum optics. And by doing that, we get a multipolar Hamiltonian where we now have expressed the interaction with the external electromagnetic field not in terms of the vector potential, but really in terms of the E and the B field. That's what this Pisa-W transformation does. And of course, this is, in the beginning, this is non-local, but if we then do a multipolar expansion of the interaction, then to lowest orders, it will again be local, and that's what we do here, and we cut it off at dipole order. And then at the last step, we introduce center of mass coordinates and get a center of mass Hamiltonian for the system. And this has exactly the structure that Clemens mentioned before. So we have one part of the Hamiltonian that describes the center of mass motion of the atom, one part that describes the internal motion of the relative degree of freedom, one part that describes the interaction of the internal degrees of freedom with the light, so AL here stands for atom light, and we have some weird cross terms that we can get rid of by a canonical transformation. And if you want to know details, I can show them to you later. And then this resulting Hamiltonian, what does it look like? Well, as I said, or as also Clemens said before in his talk, it looks like just a standard Hamiltonian for an atom in an external electromagnetic field, but now containing gravitational corrections. And it takes a simplified form if we express it in metric quantities. So if we express distances in squares of momenta and so on, really in terms of the physical spacetime metric. Because then, if we do this, then the internal atomic Hamiltonian looks like that. We have the physical spacetime metric. We use this to compute the square of the relative momentum. So that's just the usual kinetic term, p squared over 2 reduced mass, but computed with the physical spacetime metric. And we have a Coulomb term with the physical distance of the two particles. And then on top of that, we get 1 over c squared special relativistic corrections and Darwin corrections, which come from the first order magnetic field, because the particles are moving. And then we get some term with the derivative of the Newtonian potential, and that's it to this order. So everything we would expect, expressed in terms of the metric, and some correction terms. And if we write the internal Hamiltonian in this form, then the center of mass Hamiltonian takes this form. So it really takes the form of the Hamiltonian of a point particle in our metric that we chose, with the center of mass, momentum, and position. But the mass parameter in this Hamiltonian is not just the total rest mass of the system, but it is the total rest mass plus this internal energy divided by c squared. So by doing this calculation, starting really from the full relativistic theory and approximating it to order 1 over c squared, we really can derive this effective picture where the center of mass is a point particle realizing this mass defect. And so really by starting from the full relativistic theory, we get this mass defect out and don't have to put it in by hand, and we see this is the full description. And so that's nice that you can actually derive this intuitive picture that you would have guessed from, sorry, I have to make it bigger. Yeah, 5 minutes, nice, that's good. That's fine. So we can actually derive this from first principles. And yeah, as you have seen in the previous talk, this Hamiltonian we get out there can be used, or was used by Michael to describe atom interferometry. And yeah, and that's a really, really nice work. And if you want to, I can also show you the full Hamiltonian, but I won't do so now because it's really long and complicated and you don't really gain any insight from that. So now let me come to another system where you can apply such a systematic post-Newtonian expansion, namely a massive spin-half particle. So there we start from the minimally coupled Dirac equation in curved spacetime. So we assume our spacetime to have a spin structure such that we can speak about spinor fields, and then we have a covariant derivative for them, and then we just take this minimally coupled Dirac equation. And then if we look at the Dirac quantum field theory in a stationary spacetime, then the one particle sector of this quantum field theory is effectively described by positive frequency classical solutions of this Dirac equation. And so if we are just interested in low energy, one particle behavior of this theory, in the one particle behavior, then we can just focus on the positive frequency solutions. And for this one particle theory, we can then systematically derive a description from the point of view of an observer moving on some fixed world line in our spacetime. So we have this fixed world line gamma. The observer is moving on there with some spatial reference axes. And then the question is, what is the equation that this observer would write down to describe this Dirac particle? And the approximation here works in two independent steps. So as a first step, we perform an expansion in geodesic distance or space-like geodesic distance to the world line in generalized Fermi-normal coordinates. And by this, we implement a weak gravity approximation. So this is valid in a neighborhood to the world line where the distances are small compared to the curvature radius. So the curvature is small. And also where the distances are small compared to the acceleration of the observer and to the angular velocity of the frame that the observer is using. And then in the second step, we then do 1/c expansion, as I mentioned before. So in the second step, we really implement this post-Newtonian expansion, realizing slow velocities. So after this first step, we are still in the full Dirac theory, just applied to the situation of weak gravitational fields and weak inertial effects of the observer. And in the second step, we then focus on slow velocities and really a post-Newtonian expansion. And then we get a full description of this in the fully general situation where the spacetime can in general be curved, where the observer can be accelerated, and where the frame that the observer uses may be rotating. So for example, one could use this for an observer sitting on the surface of the Earth, which is rotating itself. And this was actually done by Ashkan, who is also in the audience there. I think I saw him asking a question earlier, so I know that he got to Bremen today in his master's thesis, and the paper on this just got out. And this is actually based on work by Rick Pert, who's also there. He was the main organizer of the whole RQI circuit, so thanks a lot. And Jonas Neuser. And so we extended this to a more systematic and general way of doing this approximation, and also found some errors and corrected this. And well, the main result then in the end is a full post-Newtonian Pauli Hamiltonian describing this particle from the point of view of this world line, and it looks, the first few terms look like that. So we have the standard kinetic term with the coupling to the electromagnetic field in here in the capital D. Also the electric potential is there. We have a Newtonian potential term with acceleration and with a tidal force term. We have a coupling of spin to the angular momentum of the frame. We have the special relativistic correction to kinetic energy. And then we have some curvature corrections, more acceleration corrections, and a lot more corrections that I did not write down here, because you don't really learn anything from staring at it, in my point of view. So I just wanted to make the point that you really can do this calculation in full generality, in principle to any order of expansion you want to. We stopped at this order, so at quadratic order in 1/c, and also at quadratic order in space-like distance to the world line. But in principle, you could go to higher orders, but then eventually your expansion would break down because your energies would get too high. So to conclude, I hope to have convinced you that these heuristic approximations or these heuristic ideas to derive descriptions of quantum systems under gravity are not enough, and that you really need to do it in a relativistic way, in a systematic way. And one way to do this is to do a systematic post-Newtonian expansion. And yeah, I showed you that if you do this for a two-particle hydrogenic atom, then effectively you get this mass defect picture that you would have expected probably in the beginning, but this really can be derived. And you can also apply this to a Dirac particle, and then get a Pauli Hamiltonian in the end with all effects in there. And one example application of this is an atom interferometry, which you already saw in Clemens' talk. So I wanted to give my talk before him, but now it's after this. So yeah, so you already know the application. So thanks a lot.